Hey everyone, many thanks again for a great organization. I am very happy to introduce the next speaker, Deniz Şuözer. He is a senior student at Boğaziçi University. I appreciate his effort. He was hardworking during the program and he did a good job. Especially he struggled against my annoying comments and he came through in his studies. Today he will talk about the inverse Galois problem by mainly following Eda's master thesis. You can start if you're ready. Please.
Okay. Hello everyone. Today I'm going to talk about the inverse Galois problem. Let's start by stating the problem. For a finite group G and a field K, we say that G is realizable as a Galois group over K if there's a Galois extension L over K such that the Galois group of this extension is isomorphic to G. With this, we can state the inverse Galois problem, which asks the question, is every finite group realizable as a Galois group over Q? Here's the outline of my talk. I will first show that every abelian group can be realized as a Galois group over Q. We will then move over to algebraic number theory and then show that the symmetric group Sn can be realized as a Galois group. We will then study some elliptic curves and show that the group GL2F3 can be realized as a Galois group. And then finally, I will state some other related results. We start by giving some definitions. A complex number zeta is called an nth root of unity if zeta to the n is equal to 1. And an nth root of unity is called a primitive nth root if it's not a kth root of unity for any k less than n. Now, if zeta is a primitive nth root and a is an integer coprime to n, then zeta to the a is also a primitive nth root, and this gives us every primitive nth root. The n cyclotomic polynomial is defined as the product of all x minus zeta to the a, where a is coprime to n. By our previous observation, the roots of the n cyclotomic polynomial are precisely the primitive nth root. And actually, this polynomial has integer coefficients and it's irreducible over Q. Now, one might ask about the splitting field of this polynomial. If zeta is a primitive nth root, then certainly the splitting field has to contain zeta. And if a field contains zeta, then it contains every power of zeta, so it contains every other primitive nth root. Hence, adjoining zeta to Q is enough to get the splitting field, and we call this field the n cyclotomic field. We can, and it's a standard exercise to show that the Galois group of this splitting field is isomorphic to the multiplicative integers modulo n. We can now move over to arbitrary abelian groups. If G is a finite abelian group, then we know that we can write it as a direct product of cyclic groups. So we can write G equals Z over M1Z times Z over M2Z, M2Z, and so on, all the way up to Z over MSZ. For each Mi, we choose a prime Pi that's congruent to 1 modulo Mi. And by Dirichlet's theorem on arithmetic progressions, we can choose these primes Pi to be distinct from each other. Then the group Z over Miz is a normal subgroup of Z over Pi minus 1Z. And we have a projection map from Z over Pi minus 1Z to Z over Miz. Since Pi is prime, the group Z over Pi minus 1Z is isomorphic to Z over Piz star. And if we take the direct product over all i's, we see that the group G is a subgroup of the direct product of all Z over Piz stars. Since these Pi are distinct primes, we can use the Chinese remainder theorem to claim that the product of all Z over Piz stars is isomorphic to Z over Mz star, where M is the product of all Pi. And since we had a projection map for each I, when we take the direct product, we get a projection map from Z over Mz star to the group G. So by the first isomorphism theorem, G is isomorphic to Z over Mz star over H for some normal subgroup H. The fixed field of H is an intermediate field between Q zeta M and Q. And by the fundamental theorem of Galois theory, the Galois group of this field is isomorphic to Z over MZ star over H, which we just show that is actually G. Hence, every finite abelian group is realizable as a Galois group over Q. Our method here was to take a finite abelian group and then show that it can be realized as the Galois group of an intermediate field of a cyclotomic field. The following theorem is related to this idea, and it's called the Kronecker-Weber theorem. It states that every finite abelian extension of Q is contained in a cyclotomic field. Here, abelian extension is just a Galois extension whose Galois group is an abelian group. We can now move over to algebraic number theory, and we start by giving some definitions. A number field is just a finite extension K of Q, and the ring of integers of K is defined as the set of all algebraic integers in K. Recall that an element alpha is called an algebraic integer if alpha is the root of a monic polynomial with integer coefficients. But it's not obvious that this set actually forms a ring. One usually first shows that if alpha is an algebraic integer, then Z alpha is a finitely generated Z module and goes on from there. We will denote this ring of integers by OK. And finally, a Dedekind domain is an integrally closed Noetherian ring in which every prime ideal is maximal. Let's clarify what some of these terms mean. A ring R is called an integrally closed if it contains every algebraic integer in its field of fractions. And a ring is called Noetherian ring if every ideal is finitely generated. Actually, before this, one example of Dedekind domains comes from the ring of integers. And we know that every ring, the ring of integers of every number field is a Dedekind domain. One interesting property of Dedekind domains is that every ideal in a Dedekind domain can be factored into prime ideals in a unique way after permutation. We have another definition. If K is a number field and P is a prime in Z, and this curly P is a prime in OK, then we say that curly P lies over P if the intersection of Z and curly P is equal to P. Or equivalently, we say that curly P lies over P if curly P divides P times OK. Now, if P is the prime ideal of Z, and we factorize the ideal P OK into its prime factorization by writing it as a curly P1 to the E1 times curly P2 to the E2 and so on, all the way up to curly Pn to the En. Then the ramification index of curly Pi over P is just the exponent Ei. Now, recall that the ring of integers is a Dedekind domain, and by definition, in a Dedekind domain, every prime ideal is maximal. Since this curly Pi is a prime ideal of OK, therefore the quotient OK over curly Pi is a field. Similarly, the quotient Z over P is another field. And we have a natural injection from Z over P to OK over curly Pi, which means we can view this as a field extension. And the degree of this field extension is called the inertial degree of curly Pi over P. Now, if K is a Galois extension of Q, and its Galois group is G, and we take a prime ideal curly P that lies over the prime ideal P, then the decomposition subgroup of curly P over P is the set of all automorphisms in G that fix curly P. And the inertia subgroup of curly P over P is defined as the set of all automorphisms sigma in G, such that for every A in the ring of integers of K, sigma A is congruent to A modulo curly P. This last congruency condition can be restated as sigma A minus A is in curly P for every A in OK. The decomposition subgroup is useful for computing the ramification indices and inertial degrees in general. And we have the following theorem, which states that if K is a Galois extension of Q, then the Galois group of this Galois extension is generated by the inertia groups of curly Pij over Pi, where Pi ranges over all the prime ideals of Z. And for every such prime ideal, curly Pij ranges over all the prime ideals that lie over Pi. We are now close to showing that Sn can be realized as a Galois group. First, we claim that the polynomial x to the n minus x minus 1 is irreducible over Q. The proof is a little messy, but briefly, one looks at the polynomial x to the n minus x minus 1 and its reciprocal polynomial, and shows that they don't share any common root. And it goes on from there. Now, we have the following lemma, which states that if K is the splitting field of this polynomial over Q, and curly P is the prime ideal of OK that lies over P, then the inertia subgroup of curly P over P is either trivial or it's generated by a transposition. And to prove this, one looks at the projection of the polynomial x to the n minus x minus 1 to the field OK over curly P, and then lets the inertia group act on the roots of this polynomial, and then all that's left is to count the W. Now, a theorem in group theory states that if a subgroup of Sn is transitive and it's generated by transpositions, then it's actually the whole group. And since the polynomial x to the n minus x minus 1 is irreducible, its Galois group has to be transitive. And we saw that Galois group is generated by transpositions. So we can say that the Galois group of x to the n minus x minus 1 is Sn. So we managed to realize Sn as a Galois group over Q. We now move over to the study of elliptic curves. An elliptic curve E over a field K is a projective smooth curve of genus 1 with a specified base point O. This point O is called the point at infinity. Projective curve just means that the zero set of a homogeneous polynomial, and smooth means that the partial derivatives don't vanish simultaneously. I'm not going to explain the term genus 1 since it's a rather technical term that I'm not very familiar with. And either way, in a minute, we'll see a much simpler way to describe elliptic curves. And the points on E with coordinates in K are called rational points, and they are denoted by EK. Now, here's the simpler way I was talking about. If E is an elliptic curve over a field K such that the characteristic of K isn't 2 or 3, then we can write E in the form y squared equals x cubed plus ax plus b, where a and b are in K, and the discriminant of the elliptic curve defined by minus 16 times 4a cubed plus 27b squared is non-zero. This last condition regarding the discriminant is there to ensure that we get a smooth curve, since if x0, y0 is a singular point of the elliptic curve, then x0 is actually a double root of the polynomial x cubed plus ax plus b. Now, there's a group structure on elliptic curves that make them abelian groups, with the identity element being the point at infinity that we defined at the start. And the union of the rational points with the point at infinity give us a subgroup of the elliptic curve E, and we call this group the group of rational points of E. Since we have a group in our hands, then we can investigate its group structure. If E is an elliptic curve over K and n is a positive integer, then the n-torsion subgroup of E is defined as the set of all points P in E such that n times P is O, the identity element. Or equivalently, we can define the n-torsion subgroup as the set of all points whose orders divide n. The torsion subgroup is simply the union of all n-torsion subgroups. And we know that the n-torsion subgroup is finite and in particular isomorphic to z over nz squared. Now, we have the following interesting theorem called the Mordell-Weil theorem, which states that the group of rational points of an elliptic curve is finitely generated. Since we are working in an abelian group, this implies that the group of rational points is isomorphic to the direct product of its torsion subgroup and z to the r for some integer r. This integer r is called the rank of the elliptic curve E. In general, the torsion subgroup is very well understood, and if we take the base field K to be Q, then there are only 15 possible choices for the torsion subgroup, all of which are either cyclic or direct product of two cyclic groups. On the other hand, the rank R is in general much harder to compute, and much less is known about it. It's conjectured that the rank of an elliptic curve can be arbitrarily large, but as of today, the largest known rank of the elliptic curve is 28. Here's an example for the Mordell-Weil theorem. If E is an elliptic curve over Q that's described by the non-singular equation y squared equals x cubed plus 17, then the rational points minus 2, 3, and 2, 5 generate the group of rational points, and they are linearly independent, which implies that the rank of E is 2. one can then show that the torsion subgroup is actually trivial, which implies that the group of rational is isomorphic to Z squared. Now, if E is an elliptic curve over K, we know that its torsion subgroup is a finite group. And we define the field of torsion points by adjoining the coordinates of the torsion subgroups to the field Q. And this actually gives us a Galois extension of Q. Now, if E is an elliptic curve over Q and n is an integer greater than 1, then we have an injective group homomorphism rho from the Galois group of QEn over Q to the group GL2 Z over NZ. But this injective group homomorphism isn't always surjective, so we don't always get an isomorphism between the two groups. For example, if E is the elliptic curve described by the equation y squared equals x minus 1 times x minus 2 times x minus 3, then one can show that the two torsion points are the point at infinity, 1, 0, 2, 0, and 3, 0. And note that all of them have rational coordinates, so the field QE2 is just Q, which means that the Galois group is trivial. So this is an example where rho isn't a surjective homomorphism. We are now ready to show that the group GL2F3 can be realized as a Galois group. Now, first let E be the elliptic curve described by the equation y squared equals x cubed minus x plus 1 over 4. One can show that the x coordinates of the three torsion points of E are roots of the polynomial Px, which is equal to 3x to the 4 minus 6x squared plus 3x minus 1. To show this, something called division polynomials is used. Division polynomials are recursively defined polynomials that are useful to calculate n times p for a point p in E. And if the coordinates of p are x and y, then the division polynomials give us the coordinates of n times p as rational functions of x and y. And from there, it's easy to find the n torsion points, and in particular, 3 torsion points. Now, this polynomial is a polynomial of degree 4. And in general, there are many known ways to find the splitting field of a polynomial of degree 4. One way is to look at the resolvent cubic of this polynomial and then first calculate its Galois group and then go on from there. And by doing this, it can be shown that the splitting field of P over Q is an extension of degree 24. Now, we saw previously that the field QE3 is a Galois extension of Q, and there's an injective homomorphism from its Galois group to GL2F3. Since QE3 contains the x coordinates of the 3 torsion points, it has to contain the splitting field K, so it's at least an extension of degree 24. On the other hand, the group GL2F3 has order 48, and since rho is injective, that means that the Galois group can have order either 24 or 48. We will show that it doesn't have order 24. If we take a root alpha of the polynomial P and plug it into the equation of the elliptic curve, then we get an irreducible polynomial over K, which implies that the y coordinate that corresponds to alpha isn't in K, so K can't be equal to QE3. Therefore, QE3 is an extension of degree larger than 24, which implies that it's an extension of degree 48. So we have an injective homomorphism between 2 groups of the same order, which implies that it's an isomorphism. And hence, GL2F3 can be realized as a Galois group over Q. Finally, I'll state some other results that are related to the inverse Galois problem. For example, it's known that the alternating group AN is realizable as a Galois group over Q for every n. To prove this, generally a theorem called Hilbert's irreducibility theorem is used, because one of the corollaries of that theorem is that if a finite group is realizable as a Galois group over the rational functions over Q, then it's realizable as a Galois group over Q. Another important result is that every solvable group is realizable as a Galois group over Q. And it's known that the 4 Mathieu groups that you see on the board and the monster group are realizable as Galois groups over Q. Generally, when proving that these sporadic groups are realizable as Galois groups, something called the rigidity method is used. And the main idea behind this method is that one first shows that the group is realizable as a Galois group over the rational functions over C, and then sort of moves down to show that it's realizable as a Galois group over the rational functions over the algebraic closure of Q. And then finally moves down once again to show that it's realizable as a Galois group over the rational functions over Q. As I said, from there, it follows from the Hilbert's irreducible theorem that it's realizable as a Galois group over Q. On the other hand, as far as I know, the material group M23 isn't known to be realizable as a Galois group over Q. So this problem is still an open problem. Now, one can take the statement of the inverse Galois problem and wonder what would happen if we change the base field from Q to another arbitrary field. For example, if we change Q with the rational functions over C, then it's known that every finite group is realizable as a Galois. Here are my references. Thank you all for listening.